Hey guys, welcome to another video for pre-calculus. In this video, we're discussing another calculus topic, and this one will accompany the video that we talked about finding the area under a curve. Now, this video we're going to discuss definite integrals. So let's go ahead and dive into this topic. So again, this is definite integrals, and you see the equation that we're going to be working with here. For this video, I'm going to save working out problems for now, and I just want to kind of discuss the idea, the concept of what an integral is and why we use it. And then in the next video, I'll work out a couple of problems because they're pretty lengthy. So I do want to make sure that I make a video where I just discuss the concept, and then, there'll be other longer ones later for problems. So let's go ahead and dive in. So in the previous video, you might remember our goal was to find, if we're wanting to find the area underneath the curve, we used, we used rectangles. And we noticed that this process is not a very good process because, as you can see, there's a lot of empty space in the underneath the curve. So one of the things that we had to do was we had to make our rectangles smaller. Now keep in mind that every time we make a rectangle, that the width had to be the same. It had to be consistent. Okay, and that would be the number that I picked for the x-axis. That would be my x term, or my delta x. Okay, so that width had to be consistent. But as you notice that as I add more rectangles and as the width of them gets smaller, the area that I have blank, the white area, the white space, gets smaller. So the more rectangles that I have underneath my curve, the better approximation that I got for how much that area actually was underneath the curve. Because if I want to find the area of a rectangle, that's easy, right? It's base times height, length times width, right? So if you recall from the previous problems, we just found the area of these individual rectangles, and then we added them up together. We got the sum of them together. So the smaller that the rectangle is, the more area I'm able to cover, the more precise my approximation got. So what I want to eventually do, and this is where integrals comes in, is that I want to make that width so small that it's basically you can't tell it from from its next point. It's so infinitely small that it can pretty much be said that you found the exact area underneath the curve. Okay, and this is where integrals come in. This is when I'm finding the area of a region underneath the graph, and this is all my function notation here. So on the left side of the equation, I have the integral notation, and on the right side, I have where I use my limit, because it's the same thing essentially. So let's talk about the symbols here that we have that, it looks like Greek, right? Because, well, there is a lot of Greek. But let's kind of make sense of this. You're going to have to spend some time with this and really get used to it and, absorb it, marinate in it. You may not get it right off the bat initially, but hopefully in this video I can kind of simplify the idea of it. And then in the next one, when we work problems out, it'll make sense. So by integral, just above my integral, I have highlighted in red. I'll have highlighted in red the area that I'm talking about. That's my upper limit. And then I have my lower limit, a, just below that. So just below that I have my a, my lower limit. Okay? And then I have my integral symbol, right? And so again, what this basically means is that now I'm kind of stepping into a whole nother area of math where I'm working with numbers that are so small, they're infinitely small. So that integral kind of corresponds with my infinity sign on the other side. And then, so recall that to find the area of an area, you need a length and a width, right? And so here is my y term, if you will, my f of x. And then on my limit side, it's f of x of I, okay? So I want to kind of highlight that x of sub I there, because we developed this term by using what's called a right Riemann sum. And that's going to be your lower limit a plus your I times the delta x. Now your delta x, you'll notice there, corresponds with your d of x, okay? So this d of x is actually a really important notation in calculus, because Again, this lets us know, this makes us aware that we are now dealing with infinitely small numbers, and in particular with integrals when we're looking at the area underneath the curve. Okay, because remember, the more rectangles that we use, the more precise approximation we get. So then we want our rectangles to be so infinitely small that we cover the whole area exactly. And that's what delta x is. Delta x is just my difference in x. Okay, it's the width of my rectangle. If you recall a minute ago, I said that the width of your rectangle throughout your underneath the graph has to be consistent, whether it be 1, half, a quarter, or just infinitely small, right? And we develop x by using your upper term minus your lower term divided by n. Now your n, if you look at your limit there where it says n as n approaches infinity, what's the length of my n? How many n's do I want to use? Well, recall that as I was showing you the graph when we started out with 3 rectangles, and then we went to, I believe it was like 6 or 8, and then we went to 18 rectangles. And in order to get a better area or a better approximation, we had to go to infinity rectangles. And so how many rectangles am I going to need? Well, eventually I'm going to need infinity. And this is going to be an important term because when I work problems out in the next video, it's going to help us to really simplify our formulas to figure out what the exact area is. I know this sounds like a lot and it might be confusing, but you really just need to rewatch this, keep it in mind, and I will try to really emphasize this when I'm working the problems out. Okay, so just some points to consider as we kind of land this plane here. So as we integrate or evaluate integrals, we will need the summation formulas. Okay, so that's where we had our sigma notation. Okay, this will assist us in evaluating definite integrals or the area underneath the curve. And so in order to simplify this, in order to make these equations simpler and to find the exact area, we're going to have some formulas that we're going to not need to memorize. I'm not going to make you memorize these, but we will need to have those handy because once we simplify them to one form, we're going to end up with something that looks like this, okay? So we're going to have different scenarios that are going to play out in our problems. So if you look at, for example, at the very top left, it says, your sigma notation, and it says C equals. Your most simplified version of your problem is going to look like that. Everything on the left side of each I have 8 versions of what you're going to end up with of a simplified equation. And when you get to that point, then you're going to be able to use these equations to further simplify and finally find the exact area of that's underneath the curve. Okay, so the ones that I've highlighted right now, these are the equations that you'll have when you end up with a constant. Okay, and then the next ones in yellow are the ones where you'll end up with an I or an I squared or an I cubed or to the 4th or to the 5th. And when you end up with that, remember, or not necessarily remember, but remember that you have an equation that actually equals to. Okay, and yes, somebody actually did figure this out, and yes, his last name is Riemann. Okay, so whenever you get an I or an I squared, then you know that you need to now simplify it to whatever it is on the right, and then simplify your formula. Yeah. Oh, let me back up. One more that we missed. Okay. Yeah, we talked about that. Okay, so the one that I haven't highlighted, that's just another. If you go back to your sum properties of limits, this is kind of how that plays into where you can split the limit if it's adding up together. You could split it into 2 separate limits. In this case, you could split it into 2 separate Riemann sums. So yeah, that's where we're at. So in the next video, we're actually going to work out some of these problems and hopefully make sense of this, okay? So let's get to it.